In this video, we present an overview of our paper, ShapeClipper, Scalable 3D Shape Learning from Single-View Images via Geometric and Clip-Based Consistency. How can we learn 3D shape reconstruction on a set of real-world images? Prior works achieved good reconstruction quality by assuming 3D or multi-view annotation, but such annotation is still expensive to obtain at a large scale for real-world images. Existing 3D and multi-view datasets also tend to be noisy. To make shape learning more scalable, recent work proposed to use the single-view supervision, where the shapes are learned from a set of single-view images. Although these works are much more scalable, they suffer from two major limitations, which greatly hampers the reconstruction performance. The first limitation is incorrect top-down reasoning, where the reconstructions only explain the input view, but does not accurately reconstruct the full 3D object shape. The other limitation is that these models often cannot capture low-level geometric details, such as concavities. How can we address these limitations while also remaining scalable to a wide range of object types? Our inspiration to improve the top-down reasoning comes from the text descriptions of images. We noticed that image captions often contain geometry-related information, and many nouns by themselves include characteristic shape features. On the other hand, we have seen great advances of large-scale image text modeling, such as CLIP. CLIP can extract fine-grained semantic features that correlate well with the language descriptions. Therefore, can we leverage such a powerful and generalizable model to improve 3D object reconstruction? In our study via k-nearest neighbors, we find that objects with similar clip embeddings often share similar shapes. Moreover, clip embeddings have some robustness to viewpoint changes, meaning that changes in viewpoint generally do not produce drastic changes in clip embeddings. These characteristics let us use clip to form pseudo multi-view image sets as shape supervision. This approach makes sure each predicted shape explains a set of images that correspond to these shapes, rather than only explaining the single input image. We use this insight to enforce the model to learn better top-down reasoning of the global shape structures. On the other hand, we address the limitation of poor bottom-up geometric reasoning by constraining the surface normals of the predicted shapes. Inspired by the recent success of large-scale surface normal estimation that demonstrates great generalization ability, we propose to use off-the-shelf surface normals as geometric constraint for our model. We additionally handle the noise in these off-the-shelf predictions explicitly. We now describe the architecture of our shape reconstruction model. Given the input image, the encoder infers the shape latent code S and texture latent code T. By conditioning these two codes upon the shape MLP Fs and the texture MLP Ft, we obtain the shape and texture reconstruction of the input object. Meanwhile, the viewpoint estimator estimates the input viewpoint V. The differentiable volume renderer R then renders shape and texture fields under the estimate viewpoint, so that we can compute the reconstruction losses. We further leverage our semantic constraint and geometry constraint to effectively facilitate the shape learning. More technical details can be found in the paper. In the experiments, our model achieved state-of-the-art performance on Pix 3D, Pascal 3D Plus, and open images. We also ablated our semantic and geometry constraints in detail. Please check out our paper and supplementary materials for more results and analysis. In conclusion, we present a scalable approach that learns 3D object shapes over real-world single-view images. Such scalable learning is driven by a novel clip-based shape consistency regularization that greatly facilitates the top-down understanding of the object shapes. Meanwhile, we successfully leveraged off-the-shelf geometric cues to improve single-view object shape reconstruction for the first time and handle noise effectively. We performed extensive experiments across 3 different real-world datasets and more than 60 distinct object categories. Our model demonstrates state-of-the-art performance. Thank you for your time and attention.